A basic DC motor generally has two leads coming out of it, right? And I apply a voltage, an input voltage across those two leads. So for example, if I were to apply an input motor voltage across this way, the motor will spin in a particular direction. I can also flip the polarity of that applied motor voltage. I can have my current flow in the opposite direction if I do that. And in addition, the motor will also spin in the opposite direction. So if I do this, if I'm able to flip the polarity of the voltage that I apply to those two leads, I can actually spin the motor in both directions. And of course, forward and backward, forward and reverse is going to depend very much on how you have the motor integrated into your mechatronic system. Of course, I don't typically want to actually physically sit there flipping the leads around to get my forward and reverse directions. So what I'm going to do, for example, is if I provide just a basic kind of switch in this direction and then another switch in this direction, right? If I close both of those switches and this connects to ground and this connects to V motor, I'll actually get current flow in the first direction here. So I have current flowing this way and I have a rotation of my motor that looks like this. I can set up some other switches over here so that if the first two switches are open and then these two switches close, then of course I'll have my current going in the opposite direction here, and my speed will also, my motor will also be turning in the opposite direction, because now I have my V motor across this way as opposed to these first two switches, and I'm going to label these. So this is switch 1 and switch 4. This is switch 2 and switch 3 over here. So if S1 and S4 are closed, S2 and S3 are open, I'll have current going one way. If the opposite is true, I'll have current going the other way. Right? And that allows me, this basic topology is going to allow me to provide direction control to the motor. And this particular topology has a name based on its shape. This is called an H-bridge circuit. And an H-bridge is what we're going to generally use to control motors, because it'll allow us ultimately to provide both the direction control that we're talking about here, as well as speed control if we replace these switches by transistors. Okay, so here's the same basic topology, the H-bridge circuit, in this case using MOSFETs. Right? And so I want to talk about which MOSFETs we're going to choose at different points in this circuit. Now down here, if I apply a reasonable Vin, right, I can turn this particular transistor on and off pretty easily if I make these both NMOS transistors. So these down here are going to be NMOS, and if I have, for example, some gate voltage that's higher than my threshold voltage, say my threshold voltage is like 3 volts, like we've talked about before, right? If I go up to 5 volts, I'll turn this on, basically close the switch. If I go down to 0 volts, I turn it off, effectively open the switch. And that's true for both of these. So that's pretty straightforward. What's a little more complex are these top transistors right here. So I'm going to re-sketch this over here just looking at this particular transistor, right? And this voltage down here is, if that switch is closed, is going to effectively be V motor. And so if I made this, and I'm going to call this my V gate, and I have some threshold voltage associated with this MOSFET, if I made this an NMOS transistor, so if it looked like this and it was NMOS, I'd need my gate voltage to be greater than my source voltage, in this case corresponding to V motor, plus my threshold voltage, right? And so that would typically require a fairly high gate voltage, and something that would be potentially tricky for me to provide from some digital circuit like an Arduino. Now, in contrast, if I were to make this a PMOS circuit, right, and this is now connected to V motor at top, for this case, I need my gate voltage to be less than V motor minus my V threshold here, right? So in this case, I can turn it off by applying something close to V motor to the PMOS, and I can turn it on by applying something like ground to the PMOS. So typically what we're going to do is provide PMOS transistors up on top. Alright, in this case with MOSFETs, if I apply a voltage such that this PMOS transistor is turned on at the gate, and this NMOS transistor is turned on, and these two over here are turned off, then in this case I will get a current path that looks like this, right? And I'll get some current here, and my motor will turn in, say, let's call it the forward direction, when the current is going in this direction. Now I can also reverse those, so now I'm turning off this PMOS and turning off this NMOS transistor and turning the other two on. In this case, I will get a current path that looks like this through that motor, and I'll be able to turn in the reverse direction. Now, one other thing that I didn't include here initially is the idea of including flyback diodes across these things. And I didn't sketch those originally because, at least for MOSFET transistors, those are oftentimes built into the transistor. I often have a diode path between the source and drain like this, and so that effectively gets me my diode automatically in my H-bridge circuit. If I were to use NPN and PNP transistors instead, which I can absolutely do, in that case I typically want to include an additional diode around those transistors to provide that flyback diode. Right, but you can certainly always add those diodes, and that's probably the safest thing to do, but for the most part those can be often built into the MOSFET transistor. Let's look at one half of that H-bridge, often called a half-bridge circuit, to understand how we can actually apply a voltage to these transistors in an easy way to actually drive this and provide both direction and speed control to our system. Right, so if I have a V motor, and I'm going to give myself something easy to work with, I'm going to say I have a V motor of approximately 6 volts here, and I'm going to connect the gates of the NMOS transistor and the PMOS transistor together. Right, we're going to look at what applied voltages at these gates I can apply and what will turn off the transistor and turn on the transistor. Right, so in this case, let's start with applying 0 volts here. Alright, and remember, for an NMOS transistor I need that gate voltage to be greater than my source voltage plus the threshold voltage in order to turn on. For a PMOS transistor I need that gate voltage to be less than V source minus V threshold in order to turn on. So if I'm at 0 volts here at the gate for the NMOS transistor, this one is going to be off, right? I have ground on my source, so 0 volts, which is my gate source voltage, is clearly not greater than any threshold voltage that I might have. Let's give ourselves, here for kicks, the threshold voltage for both of these of approximately 3 volts again. For the PMOS transistor, I need my gate voltage to be less than my source, in this case is my motor voltage, so 6 volts, minus my threshold voltage, which in this case is 3 volts. So if I'm at 0 volts here, this one is on, and so I can get current at least flowing in this direction through here. All right, let's now apply a 5 volt signal that you could get out of your Arduino. In this case, right, my 5 volts at my gate is not going to be less than my 6 volts minus my 3 volts. So in this case, the PMOS transistor is off, right? My gate voltage is pretty close to that motor voltage. My NMOS transistor, on the other hand, my gate voltage is above 3V threshold, above ground. So in that case, this one is on, and I can have current flowing in this direction, right here through my motor. So a potentially very simple way to provide both speed and direction control on the motor. If I want to go in one direction, I'm going to set this one to 0 volts or ground, and I'll set a PWM signal on this side. So whenever this PWM signal is high over here, I would have, for example, this transistor turned on, this one turned off, this one is always ground, so this one is always off, and this one is on. So whenever this is high, I'm going to have current flowing through my motor in this direction. Whenever it's low, these are reversed, so this one is on, this one is off, and I have no real current path through my motor, right? Both sides are effectively connected to V motor there. So to go the reverse direction and still provide speed control, I can set this side to ground. So in this case, this bottom transistor is turned off, this top one is turned on, and then I provide my PWM signal on this side. And then in that case, when this is high, similar to the other case earlier, I'll have this guy turned on, this guy turned off, and for that one, I will have a current path that looks like this through the motor, and I'll be able to speed control in the reverse direction based on this PWM signal. Right? When both are low, right, I have no current path through the motor once again. So this basic H-bridge topology is super useful anytime you want to be able to provide both speed and direction control for the motor. These are so useful. There's a lot of commercially available kind of single IC package H-bridges as well. One of those is a TI SN754410, and that is a very common one, typically kind of limited to about an amp of current. So, these are going to be very dependent on how much current you need to provide through your motor in order to get the kind of torque that you might want. Another example is the STL298 as well. And there are a lot of different motor shields that you can get, for example, for an Arduino that can allow you to use these in the future and very simply along with the Arduino as well. So those typically bake in these commercial H-bridge chips on the motor shield.